Hello and welcome back to The Space Between, one of the top astronomy podcasts in the world, and for that matter, the universe. My name's Kolby Van Camp here with Dawson Wagner. We're really excited to be back with you today. I hope you enjoyed our Josh Jury episode with our friend from the UK. That was really exciting to be able to sit down with him. Like we said at the time, you don't know a whole lot of people that are currently kind of collaborating with the BBC on a frequent basis, so that's cool. We were able to do that with him, and just a great guy as well. I thoroughly enjoyed talking to him off camera. He had some really great insights. He's been very helpful and instrumental with pushing this podcast on his social media platform, and we really appreciate that from him. Speaking of social media, if you aren't following us on Instagram, that's where we do the base of our content. You can at Space Between Pod. You can also find us on TikTok at the same link, at Space Between Pod, or the same handle, I guess I should say. But go follow us on Instagram and TikTok. There's no reason for you to not do that. And we provide really great content as well as updates for the shows that we are going to be doing, as well as the content that we're going to be making. And it's pretty exciting. Speaking of exciting content coming to you in the very near future, over the middle of March, we are going to be traveling to New Mexico to go to the Very Large Array. Dun, 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 dun. How about that? It's really exciting. We've received permission from the National Radio Astronomy Observatory to go down to the VLA and to collaborate with the scientists and with the educators that are down there and just create a bunch of content for you. I mean, Dawson's going to be taking his drone. We're going to take probably 6 or 7 cameras. We're just going to be spamming content to you throughout the entire week, and it's just really exciting and really thrilling. So please stay tuned for that. That's going to be over, I think, the second full week of March. That's our spring break, and we'll be down there. So really cool and exhilarating to be doing that kind of work, and we're excited to be bringing that content to you. So, Dawson, I mean, just any initial reactions for the VLA trip outside of just utter excitement?
Oh, it's a combination of feelings. To be able to be around that many radio telescopes and be able to kind of see what it's going to look like out there and just experience a Bortle 1 sky. I mean, I don't want to spoil anything, but woo, I'm excited.
Yeah, I've been looking at extended forecasts with my fingers crossed. Like, please don't do something dumb, and just let's not do that. So we'll just have to wait and see. And unfortunately, I've been in contact with the people, and they don't actually allow drones anywhere near the VLA, but We'll see what we can do from a distance, because I'm sure that it's protected airspace. But that doesn't mean that we can't do any more drone content and bring it to you anyway. I'm taking my telescope, doing a bunch of astrophotography. It'll be the first official Bortle 1 sky, like consensus Bortle 1 sky, that I'll have been able to, again, fingers crossed, have photographed under. So I'm excited for that. That kind of brings us into today, because we're going to be talking about not only radio telescopes, but the Very Large Array and also the Event Horizon Telescope, because some new news has come out about them in January and some of the work that they're doing at photographing the black hole at the center of Messier 87, which is a distant galaxy from us, which is pretty freaking cool. In the meantime, we would really love to connect with you through our Patreon. The trip to the VLA is kind of expensive, and we are graduate students. If you'd like to help fund that trip and be a part of the process and be a part of the collaboration that we'll be providing, including getting access to the exclusive content that we'll be putting on our Patreon, we really haven't put anything on there yet because we haven't had anybody that's become a patron. So it's kind of one of those revolving doors. At the minute we start getting people is the minute that we start putting exclusive content out there for you. So just go sign up. It's cheap, I think. I think it's really affordable. Some of the patrons, some of the Patreon people, of which I am a patron of, I mean, they have packages for like $60-$70 a month. And I'm like, man, if I could afford to fund you in that way, totally. But that's like a week's worth of dinner for me. I can't afford $60-$70 a month just to put towards your Patreon, but maybe someday. And that's not what we're asking for. I think that the maximum is like $5 or something like that. So if you want to be a part of the action, just go ahead and do it. We'd be really excited to meet you on our Discord server, which is one of the only ways that you can get a hold of that, is through our Patreon. You can check that out at www.spacebetweenpodcast.com. All right, now for the Event Horizon Telescope, radio telescopes, the VLA, all of the really cool stuff. And I guess we first need to establish what radio telescopes are, how they work. Dawson, what do you know about radio telescopes?
Right. So radio telescopes are specialized instruments designed to detect and study radio waves emitted by celestial objects in the cosmos. So they're unlike optical telescopes that observe visible light. Radio telescopes focus on longer wavelengths ranging from millimeters to meters. These instruments serve as cosmic voyagers, unveiling the hidden realms of the universe beyond what the human eye can perceive usually. So it's something that allows us to be able to expose what is there and that we're able to test that is there, but we can't see it with our regular everyday eye.
Well, and so much of the cosmos is that way.
Right.
And there was a video I was watching about this over the week. Well, I was trying to study up for this particular episode since I am not a scientist and don't know anything inherently about radio telescopes. But I thought it was very interesting that there's a whole bunch of photographical data that can be generated from radio telescopes that you can't see with the naked eye, and you can't see it with a telescope. It doesn't exist in the visual wavelengths. And so to be able to see it, you need something like a radio telescope. And you can see in this image that this scientific group had taken with the radio telescope, it's a spiral galaxy just like the Milky Way, but then the ejection plumes from the black hole at the center of this spiral galaxy become visible. And it's multiple times larger than the actual galaxy itself because of the way that this black hole is just spitting out all of the leftover junk away from it faster, or not faster than the speed of light, but almost as fast as the speed of light. And it's just blowing all of this stuff away. And you can now see it thanks to images taken by radio telescopes, which I just think is absolutely fascinating. And I've often wondered, and I haven't done a whole lot of extensive research into looking for this, but I've often wondered what it would look like if you could figure out a way to make it the same focal length as like a telescope that you use here on Earth, and then you combine the data. What would that look like to take radio telescope images and visual wavelength images and put them together, light images, and see how that comes together and what kind of detail you'd be able to get out of that?
Right. Yeah. It makes me curious about how you can combine like what we'll talk about, the parabolic dish that collects the incoming radio waves with an actual, cylinder telescope that's able to bring in light and then use that. And how you combine that data, I'm not entirely sure what that would look like or how to do that. That's above my pay grade.
Yeah, and I think that one of the keys to understanding radio telescopes is to provide some of the technical information. And we did some research before the show, and I want to provide some of you guys the technical information of what the radio telescope is and what it does. And so the radio telescope has a design and function in 3 different major areas. And so there's parabolic dishes, which Dawson just referenced, and it's the primary component of a radio telescope, which is a large parabolic dish that collects incoming radio waves. Have you ever noticed that there's like this massive dish outside of McCain at Kansas State University? And I've always kind of secretly wondered, I wonder if somebody's like taking radio telescope data from that. Like I've always wondered, because it looks really similar and it's huge. It's this big dish, and it's on the ground. Interestingly enough, it's not up high, but it points towards the sky. And so I've always wondered, is somebody using that in a radio telescope? Like, is the physics department, is that a great place for them to put it, and they just kind of put it across campus, or what's it there for? I've never known the answer to that, but I've always kind of wondered that.
Yeah, I'm pretty sure it's our NBC News satellite dish.
Yawn. That sucks. I don't want it to be NBC News. I want it to be a radio telescope.
I know. But it's similar in its design and how it looks to, an actual parabolic dish that uses as radio telescope.
Yeah, and there are some really interesting amateur radio telescope guys that build their own dishes. Like the ability to collect data from a radio telescope level is not beyond the average person, which I think is fascinating. And there's like pockets of people around the world that are amateur radio astronomers, and they can build their own little dishes. They put them up on their houses, they put them out on the ground, and they image the sky in that way, which I think is really cool. I think that's absolutely fascinating. So that's one of the main components. So you have a big parabolic dish, but then you have receivers, which are sensitive detectors that convert the collected radio waves into electrical signals. These signals can then be analyzed to reveal information about the celestial sources that emitted the radio waves. And then in the same way, you can change that data into visual components and make it look like, what does it look like, as well as what does it sound like. And then the frequency range, radio telescopes operate across a broad broad frequency range, extending from the lower radio frequencies, which have long wavelengths, to the higher radio frequencies, which have short wavelengths. And this flexibility enables astronomers to study a diverse array of cosmic phenomena. And that's just kind of the basis of how radio telescopes work, which I thought was really interesting. As a musician and as a singer, we're often discussing frequencies. And ways that, as singers especially, manipulate the frequencies that they are creating as they sing based off of tongue placement. How much are you shoving your sound through your nose? Are you putting it too far down in your throat? There's all these different ways that we discuss frequencies. In a class that I teach at K-State about audio production and audio essentials, we were looking at a parametric equalizer today, which is an effect that you can get out of Adobe Audition, which essentially allows you to remove or accentuate different frequencies. And I was sitting there in class today as I was teaching it, thinking about this is like really uber discount radio telescope kind of technology. Mm-hmm. Like really discount technology, but like the principle is the same. It's the manipulation of what frequencies. And I mean, these guys are looking at gigahertz, and I'm over here like, wow, I feel like I'm blowing the socks off Adobe Audition when I'm trying to filter something out of the 10,000 hertz range, the 10 kilohertz range. Right. And instead they're over here like, here's our gigahertz of information that we're looking at. Whatever, just get out of here. Yeah, but I thought that was really interesting.
The key thing here is like understanding when I took my remote sensing class to get my drone license, I had to learn about frequencies and wavelengths and how they're two different things. The frequency is the amount of times that the wavelength is moving. So when you see the wavelength, what it actually is just measuring, a wavelength is from one peak to another peak. And then that is the amount of times. How many times those peaks happen within however many milliseconds is then the frequency. And so it just is measuring how many of those peaks then is the frequency, and then how far are the peaks from each other is the wavelength. And so that's how I was able to figure out kind of, this is how then they then measure different light and how it hits, the different sensors of the radio telescope. Kind of cool.
Yeah. No, I thought we talked about that in a music theory class that I took because we were learning about tuning systems. And, when Mozart was around, they tuned their harpsichords this way, and certain keys sounded better than other keys because these frequencies work better together. And the A that we use at 440 hertz today was not the same A that they used 200 years ago. It was like 413 or 414 or 416 or something like that. It was a way flatter A that you would tune your orchestra to, or tune your piano or harpsichord to. So it's just interesting. And frequencies are all around us, and there's some like weird conspiracy theories about frequencies. You hear stuff about like the frequency of the earth is now allowing you to heal, or I don't know.
There's electromagnetic radiation.
Yeah, right. Yeah, right. And there's all these ideas about it, but there's also interesting science around the healing power of frequencies. Does that work? There's a scientist that I know who is experimenting right now with a Rife machine, which is a thing that like spits specific frequencies out with the potential to heal you. And I don't know what the science is around that. I'm not a physicist by any stretch of the imagination, but frequencies are always surrounding us, from the Wi-Fi routers that we have to this computer screen that I'm looking at right now, to the microphones that we're talking into, Bluetooth, our cell phone devices, our cars. The frequencies are everywhere. And I think that's just a really interesting thing, but it also necessitates these radio telescopes have to be put out way in the middle of nowhere, or you're going to get a stupid amount of like feedback and a bunch of different issues in your telescope, which is problematic.
And that's what's so interesting about the VLA, which how much they lock it down, right? Like we're going to have to go in on a day that aren't they going to like be having it down for maintenance, or it's
they have a weekly day I think it's Wednesdays. Maybe. I don't quite remember off the top of my head. It might be Thursdays. I don't remember. But one of the days is that they have like a maintenance day. And that's where people who, like us, are media, can come in and take a look at the arrays and conduct interviews and that kind of stuff. Even then, I still have to send them, actually, and I don't know if you remember this in the conversation that we had with their their key communications person. But when we go down, we're going to have to provide all of the equipment that we're taking, like the batteries that it uses, whether it's Bluetooth or not, like cell phone providers. I think like you have to say like, yes, I use, I don't know, Mint Mobile, Ryan Reynolds, my Lord and Savior, is providing me with my internet service. So yes, that's what I use. I don't quite remember, but we have to specify what those information channels are, even when the telescopes are offline, because of just how sensitive they are, which I think is fascinating.
Yeah, and it makes sense because they do need to know whatever wavelengths are coming in or out. They probably are monitoring them. They're probably trying to understand, what all is coming in and out of this space so that we can make sure that we don't have any interference with the telescopes, which makes sense. But it also goes to show just how hard it is to get rid of all these types of wavelengths and frequencies and things that are always around us.
Yeah, no, I totally agree. And in that window, I guess you could say, because there's the microwave window. Operating within the microwave window of the electromagnetic spectrum is something that these telescopes have to do. And they do that through the Earth's atmosphere. And it says in this little article that I'm reading, operating with the microwave window of the electromagnetic spectrum, where Earth's atmosphere is transparent, radio telescopes provide a clear view of celestial objects. The transparency is crucial for studying cosmic phenomena without atmospheric interference, which, if you're using visual telescopes, the larger the aperture of your telescope, the more problematic it's going to become to get rid of the interference from a wobbly atmosphere. Have you ever wondered why they put observatories so high up in the mountains? It's because they go up into a thinner part of the atmosphere, so they don't have to deal with all of the wobbly atmosphere at our level, where if we're at, Kansas is like 3,000 feet above sea level. I don't know. It's not anything substantial. I'm sure you're looking it up right now because I don't remember off the top of my head. We're not sea level, but we're really flat, and you have to go way up high to get up there.
Yeah, we're 679 feet above sea level.
Well, that shows you what I know. I was about 2,400 feet off. But that's okay. So
a couple thousand, not a big deal.
Oh, yeah.
But it really just goes
a
to
factor
show.
of 400. It's all good.
It's like range.
Scientist extraordinaire right here. What can I tell you?
Well, it is interesting though that like it requires a lot of coordination and figuring out where to put it in the first place, and then how to prevent future issues from other wavelengths and interference, and using a specific part of the spectrum in that microwave window to be able to measure whatever it is that you're viewing. Like that's so complicated. There's so many people and variables that go into that.
Yeah. And I think that it's interesting how scientists collaborate all over the world to create these arrays of telescopes, of radio telescopes, to be able to view things in greater detail. And then as the Earth turns and one place goes out of view in the sky, let's say I was trying to shoot something at the star Sirius in the northern hemisphere. By 2:00 in the morning in Kansas, at least right now, Sirius is close to the horizon, and it doesn't make sense to try and get that information from Sirius. But somebody over in Australia might have a better view of Sirius at that point. It's the southern hemisphere; they probably can't see Sirius at all. But they're able to then turn and point and look, and then you can get way more data by going around the world, which I think is really interesting. And there are a couple of unique locations that I wanted to bounce off you. I didn't know if you'd heard of them before, kind of some fun facts. But Medicina's historical role with radio telescopes. So the Medicina Radio Observatory, or sorry, it's not Medicina, it's in Italy. It's Medicina. I apologize to all of our Italian listeners. Ich spreche nur ein bisschen Deutsch. Not Italian, all right? Not Italian. I speak a little bit of German, not Italian, but I did take Italian diction because #singer. And I married an Italian. So I kind of have to be up to date. Yeah. It's things have gone off the rails when my wife's grandfather slams an entire bottle of red wine wearing his Buon Natale Christmas shirt on Christmas Eve, and then like dances all night by himself to Frank Sinatra while yelling at us in Italian.
That's amazing.
Incredible. And so it'd be the Medicina Radio Observatory in Italy has tracked lunar missions and played a role in the modern lunar exploration efforts, which is cool. So I wonder how much they're collaborated with Tesla and Elon Musk and NASA and trying to get some people up to the moon again, because that's something that is currently on the mind of the space industry, I guess you could say now. It's not the space race because it's not really a race anymore. Maybe there's a race to Mars. I guess we are racing sort of to Mars, but the space industry, I guess you could say. And then there's also the giant meter wave radio telescope, or the GMRT, in India with its large collecting area. And it's been instrumental in the discovery of precision timing of pulsars, which is cool because pulsars, I don't know if you knew this. I was reading about this earlier. Pulsars, some of them pulse with such extraordinary accuracy that they're better than atomic clocks. So if you can base your clock off of this pulsar in the middle of the sky, then you have like a perfect clock. It's even more perfect than the atomic clock, which is really cool. And so like GMRT's pulsar precision exploration is something that you can then use to measure things and measure time, which I think is interesting. And then I know you would like this one the best, but LOFAR's Alien Hunt. The Low Frequency Array explores cosmic phenomena and contributes to the search for extraterrestrial intelligence, scanning the skies for potential alien signals. Ooh. So how about them apples?
LOFAR. I kind of like that name too. LOFAR Alien Hunting.
This is my son, Lofar Wagner. Is that going to be you someday?
No, I am not naming my kids something like X or something like that, like Elon
Xenon
Musk
Wagner.
Or
Come
whatever.
on.
No, but that's interesting that there's people who are actively looking for some sort of, extraterrestrial intelligence that are out there through actual scientific means of studying signals that's would come from, low frequencies, or the low frequency array in this case. That's
and it's interesting that you bring up SETI, because SETI did what was called the SETI at Home project, and you can engage millions of people and distributed computing power through that way to collect and observe radio signals. And so the SETI at Home project engaged millions of distributed computing using spare computer power globally to process radio signals in the search for extraterrestrial intelligence, which is a really cool project using radio telescopes and then people at home. It was just kind of like, hey, you have a leftover computer? Can we use your computer? And we're just going to, it doesn't have to be particularly powerful, but we'll use some of that CPU power to try and decode some of the information. And cool. Now you're involved in SETI, in the search for extraterrestrial intelligence. Imagine if you're the person who just like randomly has an old computer running stuff for SETI and you find aliens. What? Crazy.
Well, I just think it's incredible that, so I was kind of reading up on that beforehand, and I was looking at how, in 1999, researchers at UC Berkeley kind of proposed this idea, and it started with 50,000 to about 100,000 home computers, but then has since grown to over 5.2 million participants worldwide. Like, insane. And more than 2.6 people in 226 countries are volunteering their spare processing power. It's just incredible. Like, it really goes to show like amount of people that want to be involved in something like that.
Yeah. What's the specifications for a computer? Because I have like 2 old desktops. It'd be kind of cool to be like, hey, you need my computer? And I found E.T. Like, that'd be cool.
Yeah, I'm trying to read into it, but I think we may just have to throw it up on the Patreon to let exclusive people kind of know, like, hey, if you really want to become a part of this, you can have this type of specs on your computer, and then you can maybe sign up and become a candidate to contribute towards this.
We'll put it on our Discord.
Yes, Discord. That's another great plug.
The quantum computer, our Discord server. Yeah, we'll put it. We'll run SETI through our quantum computer. I don't know if you are aware of the power of that, but we're going to do that. All
No,
right,
what-
off the
pa-
rails.
Yeah, right. The power of a quantum computer. Oh man.
Right. No, I
That's
totally get
insane.
it. But so there's some really interesting scientific discoveries and innovations that are happening with radio telescopes right now. And I think the one that is the most important to me, I'm kind of in a tie. So there's extragalactic research. So radio telescopes are revealing the intricacies of distant galaxies, allowing scientists to study their composition, structure, and dynamics, which is really cool. And then there's also gravitational wave collaboration. So radio telescopes, including those in the Event Horizon Telescope, which we'll be talking about here in just a few minutes, collaborate with gravitational wave observatories like LIGO and Virgo to create a synergistic approach to studying cosmic phenomena such as black hole mergers. So when black holes come together and then they make the explosion of gravitational waves that can now be measured, then that's really interesting. But what stands out to you, the extragalactic research or gravitational wave collaboration research? Because I see the importance of both of them.
See, for me, I feel like it's got to be the gravitational wave collaboration and being able to measure like gravitational waves just blows my mind that we could even set up an observatory to be able to measure certain things like using the Event Horizon Telescope to be able to do some sort of studying of black holes through the ways that they affect gravity. Like that is so hard to wrap my mind around on how you can actually measure gravitational waves and like that we can measure those wavelengths. That's where my mind automatically goes and what I want to learn more about.
Okay, so you're more in the gravitational camp then?
Gravitational camp, also because I feel like gravity it's like the key to some things that we have yet to figure out, like dark matter and dark energy, right? Like the gravity has to play into that. Maybe.
Sure. No, I think that makes total sense. I wish I'd had the foresight to ask Lado Samushiya when we had him on the show just a couple of months ago about radio telescopes and whether he's using radio telescopes and that kind of stuff. Because I think he is. I think some of the projects that he's working on and that he's affiliated with globally use a lot of radio telescopes, which I think is pretty interesting. And there's some fun facts that I just wanted to share. So Arecibo's radar abilities, they have the Arecibo Observatory, and it has powerful radar capabilities, allowing it to study planets in our solar system. And then there's the Golden Record's cosmic journey. So the Golden Record aboard the Voyager probe serves as a time capsule, and that's related to the way that radio telescopes work, although this article doesn't say how it's related. It just is like, yeah, some fun facts for you about radio telescopes. Is that has something to do with Voyager, but we're not going to tell you what it has to do with Voyager. So thank you for that, I guess. But then have you watched the little documentary on YouTube about the WOW signal?
Oh.
Have you, there's a couple of them, and I think I've watched all of them.
I don't think I have.
The WOW signal. Okay.
No.
Are you familiar with what the WOW signal is? Like, surely you are.
What is the WOW signal?
Oh, you're okay. So, radio telescopes. It's like a guy in the 70s. I look up the WOW signal, and while I'm telling this to you, since we're on separate computers, look this up and let me know what the year was. I don't remember. I think it's in the 70s. An astronomer working at a radio observatory, I don't remember which one, was scanning through some information, and it was like sheets and sheets and sheets of data taken because they didn't necessarily have the computing power to just run all the sheets of paper through a computer. Instead, they had to then look at it individually and manually. And they were looking, this one scientist was looking at this piece of paper, and it's a bunch of like ones and zeros. And it's, if you got over, I think it was like a 7, like it shows like 1 through 7. 7 is like, whoa, that's kind of a high power. And then once it goes beyond 7, I think it goes into like letters or something like that. And so the WOW signal is this unbelievable moment where it's like a bunch of 1s and 0s and 2s and 1s and 0s and 2s. And it's like 1, 7, B, 6, Q, R, and then it goes away. And the scientist circled it in red and wrote "wow" next to it, exclamation point. And it's never been able to be duplicated. It hasn't been able to be duplicated. And what I thought was absolutely fascinating is that the Cool World's YouTube channel, so David Kipping, who we had in the first episode of the show, he did a little documentary and an interview with a guy that's trying to recreate the WOW signal and trying to find the WOW signal. Because if he can find it again, whoa, wow, right? I mean, wow, because then you can prove that it's duplicatable. And that's this whole like search that's going on. Apparently, like the window of time to find the WOW signal based off of potential loops that it could be on is, it's like the window is closing, and so either you'll see it again or you'll never see it again. It's this weird, like they did some math around it, and they were like, we think we can predict when it would be, and it would be at this time in this area of the sky, and so they want to go and search that, but places with radio arrays like the VLA are like, we have better things to look for than spend a bunch of money to point our telescopes at this one thing and see if the WOW signal comes back again.
Right. Yeah.
So it's interesting, but it was this monumental moment because it was like he circled it. They were like aliens, wow. and then it's never come back, and that a lot of people think, well, that's because it was aliens, and then the scientific community is mostly like, well, it's just a random thing that you happen to catch a star that blew up at the right time in the right place, and there you go, and that's it. So I don't know. It's interesting.
Yeah, and it looks like the string was 6EQUJ5. Would that be right? Does that sound correct?
I mean, I was just pulling stuff out of my rear end with a potential string, and I was actually pretty close. I think I got like 3 of those letters.
Yeah, 3 of the letters, right? Yeah, but it was commonly misinterpreted as a message encoded in the radio signal and represents, in fact, the signal's intensity variation over time expressed in the particular measuring system adopted for the experiment. Yeah, and
but the whole point around that is that if it was like if it was something that was big, then if it created that much energy to register those high of letters, so like Z would be like the most powerful measuring stick that you could provide for that. If you're generating letters in the QRSTUV range, that's pretty crazy amount of power. And the question is that something that happened naturally, or was it generated power? Did something create it? And that's where like extraterrestrials come in, at least as I understand it.
Yeah, no, I think that's spot on. It just makes my mind wonder and want to then figure out how they can replicate it again, or figure out how to communicate like with that. I don't know. Frustration.
Well, it's just floating out there in the space between. So how about that? Well, coming up next, we're going to break into the VLA, our trip down there, and some of the things that we're excited to be asking questions about. And we want to hear from you. If you have questions that you want us to ask the scientists at the VLA, please let us know through our Patreon, through social media, through our website. There are multiple ways of contacting us, and we want to hear from you. Coming up next, more on the VLA and the Event Horizon Telescope here on The Space Between. In a world drowned in artificial light, the stars above are disappearing. But there's hope. Dark Sky International is on a crucial mission to restore the nighttime environment and protect communities from the harmful effects of light pollution through outreach, advocacy, and conservation. Light pollution disrupts wildlife, impacts human health, wastes money and energy, contributes to climate change, and blocks our view of the universe. Dark Sky International fights against this silent intruder, working to reclaim the beauty of our natural night landscapes. Communities, parks, and regions can earn the coveted Dark Sky Place designation, a symbol of their commitment to preserving our shared night sky. Your choice of outdoor lighting matters. Be a part of the solution, not the problem. Following responsible lighting practices, passing dark sky-friendly legislation, and advancing scientific research in this field are just some of the ways light pollution can be solved. Visit darksky.org to get involved and stand with Dark Sky International in the battle against light pollution. The stars are counting on us. So the Very Large Array, it's this large collection of telescopes in New Mexico. It's 27 radio antennas arranged in a Y-shaped configuration, and the VLA operates as a collaborative cosmic instrument. And scientists and scientific organizations and communities can generate the money to then, they have to raise it or get a private donor or something, to then create the opportunity to buy the time to use the radio telescopes, which is why the telescopes are like kind of kind of unique in that you have to buy the time to use them. It's kind of like a timeshare, but it's not like a continuous deal. It's you buy the radio telescope time for a set amount of time to do the research that you want to do, which I think is kind of an interesting, like, we have a service that we can provide you and it will cost money. Like it seems like a better capitalistic version. I don't know. Right. Maybe I don't know anything about economics, so I shouldn't be talking about capitalism on the space between. But it seems like a fairly decent way of making scientific discoveries, but at the same time, I also know it's really expensive. And a lot of these scientific communities don't have the money to be able to spend to rent time to use somewhere like the VLA. So there's kind of like this weird gap that you can't do to use it. But it's situated at an elevation of 7,000 feet, and the VLA leverages the thin atmosphere for precise radio signal detection. And the Y-shaped design allows the antennas to be moved along rail tracks, providing adaptability in configurations, which is pretty freaking cool.
Yeah, it's incredible to think the amount of people that go into it with like the 11,000 researchers that have been able to use it over the years. And I think from the thing that I was looking at, there was over 3,000 researchers and 11,000 different observing projects over the past 40 years on this, which is in 2020 when the VLA turned 40 years old, which is insane to me to think that you'd think it's more of a modern invention, but like 40 years, I mean, that's still like before double my lifetime almost. Yeah. So it just really goes to show that a lot of the things that, you know, we are discovering and still figuring out time and time again have been tested and put into trial and used in research projects to be able to discover some incredible things. And the 27 individual radio telescopes that we're going to be able to see in person are moved on these rails that you can be adjusted to be able to get the different, you know, angles of whatever it is they're observing. And it's just so cool that, you know, miles and miles of just telescopes out there is something that we're going to be able to experience.
Yeah, I thought it was especially interesting that it's like 21 miles on 4 different arms. And it offers a maximum baseline of approximately 36 kilometers, which is 22 miles in the A configuration. So if you put it in the shape of an A, then you can get up to like 21 miles of viewing distance, I guess, which is crazy. And the antennas can be moved along tracks to create those different configurations. And it was really interesting when I was doing some of the initial research on this, and I went around looking for some fun facts because I think those are cool. And it's like the VLA was brought in on train tracks. Like they had to bring it to New Mexico on train tracks. So each telescope was put on a train track and then shipped to the VLA, which I think is really cool. And it was like at the time, as if it's 40 years old in 2020, then it means it was 1980 when they started the VLA. So then the VLA,
probably late 70s. In the 70s was when they were probably rolling them and shipping them on the rails.
Right. So they had to like create new technology for these trains to be able to carry these very specific telescopes to get them to the place that they needed to be. I think that's really cool. And then they turn around and set it up on like really precise train tracks to be able to move it around and do the things that it needs to do, which is pretty fascinating.
Yeah, and the fact that it led to, you know, helping figure out the discovery of the black hole at the center of the Milky Way galaxy, or at least helping in imaging that. That's so cool to think that so many people were able to come together, you know, ship all these telescopes, these radio telescopes on rails that then ended up being able to look into the center of the thing that we're orbiting in our galaxy. Like, what a story.
Yeah. No, definitely. And that's something that I'm personally looking forward to, kind of leaning into the story behind the VLA. Not necessarily like, I mean, definitely the technical stuff and like, what are you working on now when we're down there talking with these scientists? But what I think is going to be really interesting is like, why the VLA? Why here in New Mexico outside of the obvious and that it's dark and there's stuff you can do? There's less stuff out here to get in the way of what you're trying to do. But I think that it's interesting to consider the technology involved. And when you look at 2012, they had a technology upgrade that gave them state-of-the-art receivers that had enhanced sensitivity, enabling groundbreaking discoveries. And then the upgrade marked a leap forward in the VLA's observational capabilities. And so it allowed for the observatory to be able to improve itself. It's kind of like they got a better lens to put on their telescope and see better stuff, which I think is fascinating. If you were working at the VLA, what would you be trying to discover? What would you be looking for? You're going to be the SETI guy? You're going to be like the movie Contact? The movie Contact is shot at the VLA. Like the opening part of that movie. That's why I love this movie, dude. We just need to, we haven't watched it yet. We just need to go watch it. But the VLA is like one of the main, that's the place where they discover the signal. They're like, what? And so there's this entire like contact lore behind the VLA, which I think is really interesting. And I'm like really excited to be down there to go see it. Even though it's kind of a misnomer how they discovered the signal. That's not how radio telescopes necessarily work, but it is what it is. And I just thought it was fascinating that they have kind of this pop culture kind of thing, but then it like touches on SETI and the importance of the search for extraterrestrial intelligence, but then also there's like this whole argument at the beginning of the movie about, well, you don't have the funding to do it because we need to be doing real science. And well, what is real science? You know, shouldn't science be the pursuit of things that cannot be explained and things that have yet to be discovered? Well, yes. And so who is it to say that there's a hierarchy of that? You know, who's the arbiter of scientific knowledge that gets to determine what is and is not worth studying, which is a fascinating critique of the science community that I think the movie brought about. And so I'm curious, if you were working at the VLA, what would you be studying?
If I was working at the VLA today, wait, are you talking about today? It wouldn't be in the past? Like,
if you were there today, what would you be working on?
Oh man, you know me and my obsession with black holes. I feel like I'd have to be trying to like study more black holes and figuring out, you know, where are all the black holes at? How can we study them? How can we detect that they're there? And is a radio telescope the best use for that? Or do we have to use numerous radio telescopes? You know, what are some of the things that would help us, you know, move forward in understanding these gigantic celestial objects that are at the center of what we can guess every single galaxy? I mean, that's what really just blows my mind. And so that would be what I do today. Now, if I was back in the early 30s and 40s, so what I find really interesting that I wanted to touch on is the naming of the VLA. It was Karl Jansky. So the official name of the VLA is the Karl G. Jansky Very Large Array. And this Karl Jansky, he is one of the people who was setting about and studying the problem of static interference, which disrupted Bell Telephone's transatlantic shortwave voice transmission service. That's a mouthful. Bell Telephone's transatlantic shortwave voice transmission service. And so using his antenna to track the static's peculiar timing and location in the sky, Jansky discovered that he detected the greatest static when pointing his antenna in the direction of the Milky Way, confirming that it is the source that lays beyond the Earth's solar system, that originating in the interstellar galactic material that was ultimately what was causing the static. So it's like the microwave cosmic background, and really that led to understanding, okay, how do we reduce this noisy interference, and how can we maybe use it as a tool to be able to probe and discover the other mysteries of the universe, which I think is just so fascinating. The fact that he, the one who the VLA is named after, had such a critical role in playing in that.
Yeah. In fact, it was so important that I believe his last name was turned into a measurement of radio energy. And so like a Jansky is a measurement of energy, I believe.
Really?
Yeah. So
I mean, you probably know, you're the one who's the astrophotographer more than I am.
But I mean, it means nothing to me from an astrophotography level because it's they're radio signals, and I'm not imaging. I'm imaging in the visible light spectrum.
I see.
I can't even do infrared.
Right,
I could do narrowband imaging, which is where I filter out a bunch of different light, except for very specific areas of light that nebulosity most frequently glow in. But I have no radio telescope ability, and I believe the Jansky is a measurement of radio power or something like that. It's often affiliated with radio telescopes.
It's a so it's kind of interesting because we have the International System of Units, which is what everybody is able to help the metric system things able to measure. It is a non-international system of units unit of spectral flux density or spectral irradiance. And so its use especially in radio astronomy, like you're kind of talking about, which it's hard to kind of wrap your mind around because it's dealing with the invisible. It's dealing with something we can't see, but it's there, but we're able to measure it. And that just goes to show why he is such a genius and his time in the 1930s and 40s that he was able to create these equations and measure these things with using the science that already existed. And then to form them into something that could help us make sense and be able to study things eventually like black holes. And that's just, it really goes to show the building and the process that it took to get to where we are today. And now two amateur astrophotographers who are science, communication science degree get to go see his telescope and interview people, which is so cool.
Yeah. Well, and the part of the story that makes me chuckle that you just relayed to me is that Bell Telephone is trying to come up with like the precursor to the cell phone. And Jansky's like, hold my beer. I'm going to prove to you that the Milky Way is actually calling this interference. And everybody's like, oh, oh, that's problematic.
Wait a minute.
That's what an incredible discovery. And also that kind of screws up some of the stuff that we're doing. So how do we stop the Milky Way? Like how do we get around that? That's absurd. And in fact, so I also don't know if this is correct, but I watched a documentary on this on YouTube. So, and it seemed like a reputable channel. I don't even remember the name of the documentary. I'll have to go find it, see if I can find it again. There's this interesting documentary that talked about how when like the VLA was coming online, they were having issues with radio telescopes around the world, or at least around America, with a very specific radio frequency, like radio television frequency, that was messing up all of the antennae and all of the receivers on these telescopes, and is providing a bunch of static and feedback and junk that they don't want in the background. And these scientists went and like lobbied Congress and the FCC to remove, I think it was like channel 36 or something like that from the precursor to cable television, where you had those big antenna, right? And you'd have to like mess around with the antenna on the back of your old time TV. And they successfully lobbied Congress and the FCC to just like delete this channel so that you couldn't use it on your television, and that nobody could broadcast on that channel specifically, because it just absolutely butchered all of the frequencies that were trying to be studied at the time with radio telescopes, which is a fascinating way that guys who use instruments like the VLA and around the world and the Arecibo Observatory and all the really cool stuff around the planet to come together and move their government to do something interesting. And it was like the Super Bowl was carried on this channel or something stupid like that. Like it was this big issue because it was like a NBC or a major network had control of this channel, and it would have meant like the loss of millions of dollars for this company, or a couple of scientists could look at the night sky, and they were able to successfully lobby Congress and the FCC to just delete the channel and get an alternative for this news channel. I don't quite remember, but it's something along those lines, which I think is fascinating.
What's the name of the documentary?
I don't remember. I just happened to stumble upon it on YouTube. I'll look for it once we get off the show, and I might put it on our website at spacebetweenpodcast.com. But I don't remember that off the top of my head. I just remember watching it, be like, that's fascinating. Actually, that's really cool.
Yeah, I mean, the early days of just understanding radio waves and like it almost feels sci-fi in some ways. Some people probably at the time in the 1920s and 30s with like Nikola Tesla and like all the measurements that they were able to do and like talk about, and the fact that was it Carl Jansky is often known as the father of radio astronomy because of his discovery of the extraterrestrial radio waves is just inspiring to me to think like what types of people now are doing and discovering and could be the next type of, Carl Jansky, or is that time past, is that type, they've already discovered and figured out extraterrestrial waves and now, that's the peak. We already have our father of radio astronomy. I like to think that, they're going to keep building off that, and there's going to be another father of or mother of whatever it might be. I don't know.
Yeah. No, it's cool. It's an interesting way of thinking about preserving the legacy of science and scientists that have come before us, which is a cool endeavor, at least I think. You had said something momentarily ago about how you thought it was interesting that radio telescopes can see things which aren't visible to us. Like they can see the invisible, which I think is fascinating. And that's going to tie us very beautifully into the final part of today's episode on the podcast about the Event Horizon Telescope. And this is where it gets really interesting because this is from sciencenews.com. And astronomers have snapped a new photo of the black hole in the galaxy Messier 87. And so the Event Horizon Telescope is a collection of telescopes around the world of radio telescopes that all collectively pointed at the same thing for years. It took years and years and petabytes of data to be able to create an image of this black hole. And it's like you're imaging something that doesn't emit light, which is crazy. And the absurdist part of this to me is that Messier 87's heart, which is this black hole, is about 55 million light years from Earth. And they were able to generate a fairly high definition picture of the shadow of this black hole and its accretion disk, which is just unbelievable. And so this article is from this January 18th of this year. So we're a little bit behind the curve. It was almost a month ago where they brought this out. A guy named Adam Mann for sciencenews.org, apologies, I think I said sciencenews.com. Sciencenews.org wrote this article, and the image shows data from 2017, and then they had the added data from 2018, and you can see that things in the accretion disk, light moved. And it's kind of like, oh, that's really cool, where you can see these images where the light's on one side and now it's the bulges on the other side based off of the new data that they've been taking with the Event Horizon Telescope. And I just thought that it was fascinating to read about the way that this has just become a scientific pursuit to not only take an image of something that can't be seen because the black hole sucks in light. Not only does it not emit light, it removes light from around it, which is absurd. But it also validates different scientific principles, which I think is pretty unique. And the article says that it says a bright ring and the black hole's shadow appear almost exactly the same size as before. This helps confirm that Messier 87's black hole is the type predicted by Einstein's general theory of relativity and not some more exotic or unexpected variety, which a professor from Princeton University was quoted saying, which I think is important for the scientific community because it validates theories that we have going on right now that are working their way towards becoming laws. And some of it's like, we had to take a picture. Like, how do we test this without being able to see it? And so they were finally able to take some pictures of it and then see how it moved and see how it changed. They were able to predict that change, which is really cool.
Yeah. And not only have it be just from one perspective, but the fact that it's so many different telescopes that are around the Earth that are able to create a virtual Earth-sized telescope in some extent. It's the biggest telescope that we've ever been able to imagine. But then having all these combined using multiple independent techniques and efforts that are able to eliminate algorithmic bias, parameter selection, and human bias. Because I feel like all those are so often come into play when we're trying to figure out something that is really complicated that we're not able to understand. But then we think, oh, well, this must just be shaped in a specific way to get us to be convinced that, oh, it is real. But in reality, no, it's independent research that's done, then combined and tested over and over and over. And so that's why when it comes down to, yes, there is an actual photo of a black hole that exists, you can cross-check and verify and be like, no, there's no algorithmic bias. There's, making sure it's proof against parameter selection or human bias that comes into play. And that's the thing that inspires me the most, I think, about the Event Horizon Telescope, is the fact that it's able to put that on full display with the amount of people that are involved in it.
Yeah. We talked with Trevor Jones a couple episodes ago from Astro Backyard about just the importance of scientific discoveries and things that happen real time that are distributed all over the world that are like really monumental kind of moments in the scientific community. That's like, wow, that's cool. And how it affects a generation of people. There was a whole generation of people that wanted to be astronauts because they were alive, they were kids when Neil Armstrong landed on the moon. And I'm just curious. So the iconic black hole picture was delivered to the world's imagination just a couple of years ago. I think it was 2018 when it was sent out to the world. To you, how does that highlight the universal curiosity and wonder ignited by cosmic discoveries? And does it do that for you as well?
Oh, I feel like it really just puts on full display the amount of possibilities and the things that can be done when you work together with people who you may not even be able to talk as the same language, but through the form of translating and being able to use technology to grow and figure out how to create, almost like scientific poetry, as, like some might say the Event Horizon Telescope is. It's so beautiful in that way to bring together differences in people around a common morale of knowing that we are just so small in the bigger grand scope of things, but the fact that we can understand that in the first place is beautiful, and it is what inspires me to want to figure out how these things work. Why are they trying to take a photo of a black hole? What is that going to do for my everyday life? Probably not much if I really think of it, if I'm not just gonna be curious. Yeah, it's not gonna affect me. I can go about my day to day. But in the bigger grand scheme of things, the fact that we can have this capability and the access to this knowledge is what brings me joy and happiness, and is what makes me passionate about astronomy.
That's cool. It's a good response. I agree with everything that you said. I'm kind of in the same boat, and neither of us had the scientific expertise to be able to sit down and engage with this at a really heady level. Right. But it's really cool to be able to sit back and look at the pictures and say, wow, I was alive when the first picture of a black hole was taken. That's kind of a cool thing to be able to say.
Statement. That's a crazy statement.
My grandmother just this last January turned 99. Her first job was putting parachutes on little bombs that the Americans dropped on Germany in World War II. And, she's one of the few people alive today who can say, I remember when FDR got on the radio and said that we were bombed by Pearl Harbor. By the Japanese at Pearl Harbor. We weren't bombed by Pearl Harbor. We were bombed at Pearl Harbor. And there's moments. And I don't think that the image of the black hole has the same immediate lasting impact on as many people as the bombing of Pearl Harbor did, because it resulted in millions of deaths and the creation of the atomic bomb, and it resulted in all of this wild stuff. But you look back on moments in your life and you say, I was there for that. That's actually really cool. And when we're old men someday talking to our grandchildren, we'll be like, well, I remember in 2018, I was 19 years old when the first, image of the black hole came out, and now you guys create black holes in your labs. I don't know. Like, I have no idea. I have no idea what it's going to come out to be.
It just goes to show just how much it can bring people together in all the chaos, kind of like you're describing, of the world and wars and all these things that have happened through our history that we read about and hear about that kind of makes us kind of fear things. This does kind of the opposite, but still has that sense of fear and wonder, because you're like, wait, what's a black hole? Oh, wow, it's something that you could become spaghettified in and like that you would die if you go into, theoretically. But then at the same time,
or would you?
Or would you? Yeah, exactly. We don't know because we've never sent anything actually down into it, but we know that it exists. And that is the thing that blows my mind the most about all this, is the fact that we are able to bring together so many people to know that it exists and confirm that through science and using science that has been tested time and time again and across numerous cultures and numerous languages. And it brings all these different people together from different parts of the world that then is able to come to a common agreement instead of what Pearl Harbor and all those wars and things did, which was the opposite in some ways.
Yeah, no, I agree. It's fascinating to me that the technology is within our grasp and that we're going to go see it. We're going to go see it in March. If you would like to know things about the VLA, if you have questions, please DM us on Instagram at SpaceBetweenPod. You can DM us on TikTok at SpaceBetweenPod. If you'd like to send us a message through our website, we'll get it in our email. You can do that at www.spacebetweenpodcast.com. If you want to send us an email, you can do that at spacebetweenpod@outlook.com. There's so many options for you to get a hold of us, and we want to be able to create content for you. That's exciting, but we also want you to have a say in the content. Folks, just send us a note. It's not hard. Just do it. We want to hear from you. We want to help create the content that you want to see. We want to collaborate with you in that way. So I'm really excited for it. Go check us out on Patreon. That'll help us fund our trip just a little bit more. I mean, we've already funded the trip, but it'll help take the pressure, I guess, off of the funding that it took to go down to New Mexico, spend a week down there, do all the stuff that we're doing to be able to speak with these scientists. Totally worth it. I have my own ulterior motives for doing that outside of just the podcast, but it's mainly for you, the listener. And so we're excited to bring that content for you and to travel for the first time in a media-based setting for the podcast. So any parting words, Dawson, as we wrap this up?
Oh, thankful for all our listeners out there and giving us the ability and to listen to the chaos of what astronomy and the science might be, even if you might not understand it. You know, being willing just to take the step into listening to this is a good thing, and I think a positive for your imagination and being able to understand what's out there, because we're here to help you understand the complex things that we're trying to understand and communicate better about.
Yeah, absolutely. Well, with all things being equal, the simplest answer is probably the correct one. And Occam's razor is my friend. So there we go. There we go. Well, appreciate you tuning in to us today. Go check us out, spacebetweenpodcast.com, Insta and TikTok, spacebetweenpod. Send us an email, spacebetweenpod@outlook.com. We appreciate you tuning in. Keep looking up. You've been listening to The Space Between.